The File Descriptor Table Management System provides a kernel-level interface for tracking open file resources across process contexts. The table maintains a sparse array structure with entries referenced by integer identifiers. Each entry contains metadata including file offset, access mode flags, and a node reference. The descriptor allocation follows a first available strategy, beginning at index 0 and incrementing sequentially. Descriptors 0, 1, and 2 are reserved for standard input, output, and error streams respectively. Table capacity is determined at process initialization and remains fixed throughout the process lifetime. The default capacity is typically 1024 entries on most architectures, though this value is configurable at system configuration time. Requests to allocate descriptors beyond current capacity return an error code indicating resource exhaustion. The implementation maintains a doubly linked free list of available slots to reduce allocation latency. Descriptors are tracked in process-specific kernel memory alongside other runtime metadata. When a file descriptor is allocated via the open system call, the kernel performs several validation steps. The file path is resolved through the namespace hierarchy, traversing symlink entries and checking directory permissions at each level. Once the target node is located, its open count is incremented atomically. The file offset pointer is initialized to 0 for regular files, or to the appropriate start position for special files. The access mode flags are stored according to the caller's request. File offset management operates independently for each descriptor instance. Seeking operations modify the offset without affecting other descriptors pointing to the same underlying file. The offset is stored as a 64-bit unsigned integer, supporting files larger than 2 terabytes on appropriate systems. Offset operations are atomic on systems with native 64-bit load and store instructions. On systems lacking this capability, offset modification acquires a descriptor-level read-write lock. The close operation removes a descriptor entry from the table and decrements the inode open count. If the open count reaches 0 and the file has been marked for deletion, the inode is deallocated and its storage reclaimed. Pending write buffers are flushed to persistent storage prior to descriptor removal. The descriptor slot is returned to the free list for subsequent allocation. The close operation may block if buffer flush operations require I/O completion. Duplication operations create additional references to the same underlying file. The dup and dup2 calls copy the descriptor table entry while incrementing the inode open count. Multiple descriptors pointing to the same file maintain separate offset pointers. Changes to file access mode through one descriptor do not affect other descriptors. The duplication operation returns a new descriptor integer or an error code on failure. Flags associated with descriptors control behavior across system calls. The close-on-exec flag determines whether a descriptor survives process image replacement via the exec system call. The non-blocking flag modifies I/O operations to return immediately with an error rather than blocking. The append-only flag forces all write operations to append at the current file end regardless of offset position. These flags occupy a separate byte in the descriptor entry and may be modified independently of the file state. Read operations utilize the current file offset to determine starting position. The kernel transfers data from the file to the caller-provided buffer in user memory. The number of bytes actually transferred is returned, which may be less than requested. The offset is incremented by the number of bytes transferred. End of file is signaled by a 0-byte return on a valid descriptor. Read operations acquire a file-level shared lock to prevent concurrent metadata modifications. Write operations similarly use the current offset as the starting position unless the append-only flag is set. Data is transferred from the user buffer to the file or underlying device. For regular files, if the write extends past the current end, the file size is expanded. Write operations are cached in system buffers and do not guarantee immediate disk storage. Fsync and related operations force buffer flushing when durability is required. Write operations acquire a file-level exclusive lock. Descriptor reference counting maintains an open count for each inode to track active uses. When a process terminates, all descriptors in its table are closed automatically, decrementing open counts. Shared descriptors across multiple processes are counted separately, preventing premature resource deallocation. The open count is stored as an atomic integer in the inode structure. Unlink operations on open files decrement the link count, but defer actual deletion until open count reaches 0. Special file handling applies different semantics to device nodes and pipes. Device descriptors bypass the file offset mechanism and instead interact with the device driver directly. Pipe descriptors maintain internal buffer structures separate from the inode system. Socket descriptors represent network connections and support protocol-specific operations. Regular file operations do not apply to these special descriptor types. The descriptor table distinguishes file type through flags in the entry. Seek operations modify the file offset to arbitrary positions within the file. The whence parameter specifies the reference point, file beginning, current offset, or file end. Seeking past the file end creates a sparse file with 0 filled gaps. Seeking past the maximum offset value returns an error. Negative offsets are rejected. Seek operations do not perform I/O and return immediately with the new offset value. Getter-gather operations accept multiple buffer references for single I/O requests. The read event write calls process arrays of buffer pointers and lengths sequentially. The buffers are processed in order without gaps between them. Vector operations reduce system call overhead compared to multiple individual operations. The total byte count across all vectors may not exceed the maximum single request size. Vector operations maintain sequential offset advancement as if performed through single continuous buffer. Polling operations monitor multiple descriptors for readiness conditions. The select and poll system calls block until at least one monitor descriptor becomes readable, writable, or reports an error condition. The kernel maintains ready queues for each monitor descriptor type. Event notification is asynchronous and does not distinguish between multiple events on the same descriptor. Applications must requery readiness after handling each event. Polling operations return immediately if any descriptor is already in the requested state. File locking provides advisory mutual exclusion across descriptor contexts. The flock operation acquires a shared or exclusive lock on the entire file. The FCNTL lock mechanism supports byte range locks with more granular control. Locks are associated with the file, not the descriptor, preventing lock inheritance through duplication. Releasing a lock requires explicit operation or descriptor closure. Lock operations do not block ongoing I/O on the file. Error handling returns negative integers with error set to specific error codes. EBEDIV indicates an invalid or closed descriptor. EXIS indicates insufficient permissions. EGAIN indicates the operation would block all non-blocking descriptors. INVAL indicates invalid parameter values. OVERFLOW indicates numeric overflow. ENDFILE indicates system-wide descriptor exhaustion. ENDFILE indicates per process table exhaustion. All error returns preserve the descriptor state without modifications. Application code should check all return values before proceeding.